good. Yeah, maybe it's good. Right? Okay, so what I want to do today is finish the Gramschmidt business, the Gramschmidt process, Gramschmidt orthonormalization. And then for the midterm, you guys wanted to do some practice problems or review thing. So I decided I will do it in the class, maybe today. I hope we'll start today and probably finish it on Friday. Because for the recitation, there should still help you with the project. Like you still have to do a project on Friday. Maybe like a lot right now, but can make it. Yes, I was just saying that I will do the practice problems for the midterm. I posted them on Piazza if you noticed that. I created some practice problems so you have sort of an idea what's going on, what the midterm will be like, what sort of problems you should prepare for. The best way to prepare for them is by like going through the Gilbert-Strang's textbook and doing some of the problems from the textbook. And the problems I will discuss after I finish Gramschmidt, they will be like sample problems. I also took them from Strang's textbook, so that will give you an idea. Oh, on the midterm, there will be nothing allowed except for pen and paper and your brain. Huh?
Calculator, no.
What's that?
Will a calculator be allowed?
No, you don't really need a calculator. If you need a calculator, you are doing something wrong. Let me put it this way. No, you're like, yeah, there will be like some basic mathematics, like 12 minus 6. But you shouldn't like be doing anything more complicated than that. So if you are doing that, then you are probably doing it wrong. I guess the biggest high-level advice regarding the midterm is it's easy to get stuck somewhere on like one problem and like spend a lot of time on it and actually get it wrong. So like I would like you not to do that. It's better if you see it's not going anywhere, if you're not sure, then just like move to another example because there won't be a whole lot of time. That's why also it's good to do some practice stuff. So we will do the practice midterm, I guess, in a little bit. Have you looked at it? I posted on Piazza like yesterday, I think, when I prepared it. So you can check it out. It's there. If you are online, you can check it like right now. All right, but let me first deal with the Gramschmidt. So we are and these squares. So this is what I discussed. So ignore the top part. I will ignore it for you by doing this. So Gramschmidt process is a very cool thing. It's an algorithm which starts with n linearly independent vectors from m-dimensional vector space. The m can be arbitrary, but except that you can already, let's start practicing already now. What can you tell me about the m? If I tell you there is n linearly independent vectors existing in an m-dimensional space, what can you tell me about the m? That m is at least n, right? Otherwise there couldn't be n linearly independent vectors existing in it, right? So things like this you should be able to answer. So this is the input, n linearly independent vectors in some m-dimensional linear space. And the output will be n orthonormal vectors, which have the cool property that they span the same space as the input vectors. So the span of these two subspaces, the span of A1 to AN, is the same as the span of Q1 to QN. And how the Gramschmidt works, that's what we were discussing on Monday. It first creates an orthogonal basis. And then from orthogonal, it's simple to create an orthonormal basis, right? The second step is just normalizing all of these vectors. So the second step is trivial. What it all is about the first step, so how to turn this n linearly independent vectors into orthogonal vectors. And I was describing on the case when n is 3, so I have just 3 vectors. And the idea of the Gramschmidt process, that's also a useful thing to remember, is that it first starts with the first one, so it does actually nothing to it, just commits the first A1 directly to the basis. And then the second one, it takes the second one and subtracts the projection of the second one onto the basis of the one-dimensional subspace spanned by B1. So this is what this means. You should remember by now that this is a projection matrix, projection on a subspace, the B1 B1T divided by B1T B1. And geometrically what it means is that I take A2 and I don't like the component in the B1 direction, so this is my B1 direction. So I subtract off the component in the B1 direction. And what I get is A2 minus this, so this is my projection onto the B1 direction, and I get B2. And that's my second basis vector. That's my second orthogonal vector. That's the second vector that Gramschmidt produces. And the third one, it's the same idea. Then I take my A3, so I take a new vector. I grab a new vector from the input, and I subtract its projection onto B1 and onto B2. So you could like imagine if this was like A3 in 3D, like sticking out of it, something like that. Then I would take the components in B1 and B2 and project them away. So I would be only left with the orthogonal component, something that, that's funny, something that like sticks out perpendicularly out of the plane. Do you see that? It's always good to have like geometric intuition behind these formulas because that helps you a lot. Even with like the problems you will be solving in the midterm, like being able to like imagine like what does it mean in terms of lines and subspaces or planes in 3D. It's very helpful. So let me do a numerical example of Gramschmidt so you get a better idea. So you should already have a geometric idea, but let's do a numerical idea. So let's just pick some 3 linearly independent vectors and run the Gramschmidt on it, on the paper. So this will be my A1. So this is my input. 2, 0, and -2. That's a little bit, okay. And A3 will be 3, -3, and 3. So this is my input. I just want to demonstrate to you how the Gramschmidt is going to work. So, Gramschmidt. So first, it takes A1 and just assigns it to B1. So B1, it's already done, right? It's 1, -1, and 0. That's it. That was simple, right? So for B2, what do we for B2? So we take A2 and we subtract off the component, B1, B1T, B1T, B1, A2, right? So if we plug in the numbers, what do we get? So this is my A2. So how can I compute this? B1, B1T, A2, what it's going to be? So I can compute it as B1, B1T, A2, right? So that's just a dot product. And what is B1T, A2? So this is B1, this is A2. So what is going to be the dot product? So if I write it like this, B1T, A2, anybody? Just yell it, that's fine. I think it's 2, right? It's B1 is this, and this is A2. So that's 2. So let me write it this way. I will write it as minus. So this is on the top. So this is 2 divided by B1T. B1 is how much? It's also 2, right? This is B1. This is the square length of B1, right? So it's 1 plus 1. And this is scaled by B1. Yes, by this B1, right? Here I did the B1T A2. This was the one dot product, and the B1T B1 was the other dot product. So this B1T A2 was 2. This B1T B1 was also 2, and this B1 is still a vector. So this is 1, -1, and 0. So what I have to do is do 2, 0, -2, -1, -1, 0. Which will be 1, 1, -2, right? So this is also the type of calculations you will be doing at the midterm. So like doing calculators probably slow you down, right? If you were using it. So this is B1, this is B2. Let's do B3. So B3 was, we take A3, that's this guy, and we subtract the same drill again, the projection on B1, A3. Don't forget that now we are working on the third vector. And the same thing for B2. So the projection on the B2 line. So if we plug in, so let me first compute the dot product here. So the B1T A3, how much is it going to be? Help me. B1T A3. So I think it's going to be 6. Do you agree? And B1T B1, I think I already had there somewhere. Let me write it again. B1T B1 is still 2, right? So that was this part. This is the B1T A3. Because it's associative, I can do this trick, right? I could also like write down this matrix, but that would take more work, because this would be a 3 by 3 matrix. So I don't want to do it. I want to do it the easier way, where I first compute the dot product and then just hit it by a vector as a scalar product. Okay, so let me actually put it here. So A3 is 3 minus 3, 3. And here we have what? So we have B1T A3, that was 6 divided by 2 times B1. B1 is 1 minus 1, 0. Right? And this guy is how much? So this is B2 transpose A3. So this is A3. There is my B2. So what is the dot product going to be? So this is 3 minus 3, that cancels. So I think it is minus 6. And B2T B2, what that is going to be? So the square norm of B2, 1, 1, and 4. So that is also 6. That looks promising. So this is minus 6 over 6 times B2, which is 1, 1, and minus 2. And here we will see if I get it all right. So this is just 3. This is just 1, right? So all to let me write it out properly. So this is minus 3, 1, minus 1, 0, and this is minus 1, 1, minus 2. So if I put it all together, I have 3 minus 3 minus 1, that's going to be minus 1. Is that right? I'm not sure if I did it all completely correctly. Let's see, minus 3 plus 3, that disappears, and there's another minus 1. And this is 3 plus 2 is 5. That looks a little weird to me. Maybe I made a mistake somewhere. So the way we should check for mistakes is by checking that these vectors are really orthogonal. I think I made some mistake in the B3. Well, let's see if B1 transpose B2. That should be 0, right? If they are orthogonal. And if I do B1 transpose B2, that is correct, right? There I get 0. But this B3, B3 times B1 is fine, but B3 times B2, I don't think it's fine. That does not give me 0. So that means I must have made a mistake in computing the B3 somewhere. Huh, funny. I think I know where. B2? No, I think the problem is that when I was computing, so this was B2A3 is minus 6. That is fine, but I was subtracting it, so here should have been plus. right? Because there is minuses are from Gramschmidt, and there was another minus, and I got confused. So, and those are like the typical mistakes in you do. I don't think calculator would help you a lot with things like this. So let's see if now it adds up correctly. So this was wrong because I need to add it here. So let's see what we get now. So we get 3 minus 3 is 1. Minus 3 plus 3 is 0 is 1. And this is 3. Yeah, that looks much better. Because now, let's see. So this is my correct B3. And let's see if it works. If we do dot product of B1 and B3, we get 0, right? That's this and this. That's 0. And if we do B2, B3, we get what? We get 2 minus 2, so that's also 0. So that's nice. So these guys really are orthogonal. So this was the first step of Gramschmidt. So this was like the first phase. And the second phase, that just means to produce the Q, the actual orthonormal vectors, which are just normalized B's. Right? So in this case, what is the norm of B1? Just yell at me. Huh?
2.
Square root of 2? Yeah. The actual norm, not norm squared. So norm of B2 can just, yeah, square root of 6. And of B3 is square root of 3, right? So if you want, I can write it. I don't think, well, let me do it. So Q1 is 1 over the reciprocal square root times B1, 1 minus 1, 0. Q2 is 1 over square root of 6 times B2, that's this guy, 1, 1 minus 2. And Q3 is 1 over this times 1, 1, 1. And now if I make a matrix Q1, Q2, Q3, in other words, I put these numbers, I stack them in a matrix, then this is an orthonormal matrix. So if I call this Q, because it's also square in this case, then I have Q, QTQ is Q, QT is identity. That's only because it's square. That's because it's a special case that we had 3 vectors in 3D. So we get a basis of the entire space. If we had 3 vectors in 4D, this would not create basis of the entire space. It would only create a basis of a 3-dimensional subspace. Just in 3D, we only have 3 dimensions, so 3 linearly independent vectors, they form a basis for the entire space. If it was in 4D, they would constitute the basis only for a 3-dimensional subspace. Make sense? All right, so this is example of Gramschmidt, and you were asking what is the Gramschmidt good for? So here is what is it good for, or one of the things it's good for. It's good for many things, but because I was previously talking about least squares, my motivation sort of was if the matrix to begin with is it has orthogonal columns, then least squares become really simple because I don't have any matrix to invert, right? So the idea, so one of the motivations for Gramschmidt was, okay, if we don't have an matrix with orthogonal columns, can we like do something to convert it to matrix with orthogonal columns? And that's exactly what Gramschmidt does. So this ideas can be formalized in what is called the QR factorization. I was trying to like sort of quickly explain it the last time, but I don't think it worked so well. So let me try to explain more carefully now. So QR factorization is another factorization of a matrix. You give it a matrix on the input. So in this case, it would be matrix of with linearly independent columns, and would be like again typically the thin, tall matrix. And this decomposes into an matrix with orthonormal columns and an upper triangular matrix. And one way to like arrive to QR decomposition is by looking at what Gramschmidt does. So now you should have still in memory the Gramschmidt algorithm. So the idea was that the Q1 is chosen such that the first input vector, A1 is the first input vector, is in the span of Q1, right? The Q1 is really just rescaled A1, so in that case it is trivial, right? Then the second input vector is A2, and Gramschmidt chooses Q2 in such a way that A2 is in the span of Q1 and Q2. It's in the subspace generated by Q1 and Q2, right? Basically because we just take A2 and we subtract the part which is already in Q1, but that doesn't change the span, right? So, so A2 will still be generated by Q1 and Q2. You can still write it as a linear combination of Q1 and Q2. And the same argument goes for all the input vectors, right? For 3, I have to take the first 3. For 4, I would have to take the first 4. So here you can sort of intuitively see where this upper triangle comes from, right? But let me go through it a little more slowly. Oh, I can get rid of this arrow. So because A1 is in span of Q1, that means that I can just recover it by projection, right? Because now I have Q1, Q2, Q3, and so on up to Qn is an orthonormal basis, right? So coordinates with respect to orthonormal basis, I just get by dot product, right? That's very simple. So if I want the coordinate of the first one, I just dot product it with Q1, and if I multiply with Q1, I have to get A1 back, right? Those are just coordinates with respect to an orthonormal basis. Now the same thing goes for A2, except that now A2 is in the span of Q1 and Q2. So here I have to project it, the 8, I'm taking A2 and projecting to Q1 and Q2. And this is a scalar which is the coordinate with respect to these two orthonormal vectors. And this gives me back A2. The same idea for A3 and so on up to AN. So this is why these equations are true. And if you look at it carefully, the set of these equations, I guess this should really be not 5 but n, right? Because this goes on and on. The n could be like a million, doesn't matter, it will still work. So we can write this set of equations in matrix notation. That's our favorite thing to do. And this will be the QR decomposition. So if I put these, so the A are column vectors. So if I put them in a matrix like this, so these are the columns, and call this matrix capital A matrix, and do the same thing for the Q's. The Q's are the result of the Gramschmidt, including the normalization. And here are the dot products, the coordinates. So you can easily see that if I do this matrix product, like don't be fooled that these are vectors. So this is an actual matrix. This is not just a vector, right? But it multiplies the same way as if it was a vector. So this means that Q1 gets multiplied with this. The second column will be Q1 times this, Q2 times this. So this is exactly the second equation, and so on. Do you see that relationship? Cool. So if I call this Q and this R, then I obtain my QR decomposition, because this matrix has orthonormal columns, and this matrix is upper triangular. And this can be constructed by Gramschmidt for any matrix A as long as the columns are linearly independent. I think you can actually do something even if they are linearly dependent, but then it becomes a little bit more funny, so I'm not gonna go into that now. I know that the Gramschmidt can be fixed, so it can accept linearly dependent input, but you have to like specifically care about it, because you see what could be a problem in the Gramschmidt algorithm where Gramschmidt will fail. That's actually a good exercise to think about. if I put back the Gramschmidt process, so here is how I'm computing the b's, right? I could keep going on and on. How this can fail? So what if I have incorrect input? What if I give it by mistake maybe linearly dependent vectors? What's gonna happen in the algorithm? What is going to happen is that one of these vectors is going to be 0. And then in the next step, it means that I will want to divide by its length, which will be 0. That's not good to divide by 0. So there will be some nan thing going on. And it can be fixed by specifically checking for the 0 and then removing that vector from the output. Actually, I think it works like this, that the Gramschmidt will fail at that vector AK, such that AK is a linear combination of A1, A2 to AK minus 1. But those are, that could be considered advanced, so you don't have to remember that. Just a good exercise to think about. Okay, so let's assume everything is cool and we have linearly independent columns to begin with, so Gramschmidt just flies. And we get a QR factorization. Oh, by the way, if you do QR in MATLAB or somewhere, so first of all, you should know that MATLAB is not actually doing anything. It's only calling LAPACK, which is doing all the smart stuff, like all the numerical business. LAPACK is fairly old, but really good linear algebra package. And it's not actually computing. If you call the QR routine, it's not doing Gramschmidt. There are better numerical routines, because as you know from LU, when we are talking about Gaussian elimination, you have to be careful about these numerical issues. So there are actually better numerical algorithms for computing QR than Gramschmidt. There is a method of householder reflections, but that's an advanced stuff. It's still good to understand the Gramschmidt process, and it still works. With just a few numerical tricks, it can work fairly well. I did implement it previously for a real project, and it works surprisingly well. So this is just a disclaimer. It's not just all about Gramschmidt. Okay, but no matter which way we computed the QR decomposition, it has these properties, right? What we are talking about is the numerical thing, how perfectly orthonormal the columns of Q will be, right? If you have a not so precise Gramschmidt algorithm, if you just implement actually exactly what I told you, then you will not have super orthonormal columns. They will be okay-ish orthonormal, but there will be some errors, right? What I mean by the errors is that Q1, TQ2 will not be exactly 0, but might be 0, 0, 0, 0, 0, 1 or something like that, right? And then it's not super. This is the quality of orthogonal orthogonality. But I guess that does not really concern you at this point. Maybe it will concern you at some later point. I actually run into that in practice. I was why is it not perfectly orthogonal columns? And it's aha, there's numerical issues in Gramschmidt, and you have to play some numerical tricks. There's called modified Gramschmidt thing, which is a little bit more stable. And even more stable would be the household reflections stuff. Okay, enough of numerical rant. And let's see, how do we apply QR in these squares? I guess that's what you were wondering the last time. What is it good for? So here is how we can apply it to elegantly solve the least squares problem. So we know that the least squares problem leads us to the system, which is sometimes called the normal equations system. That's what we were discussing in detail previously. So that's this system. And if we have linearly independent columns of A, we can apply the QR decomposition, where Q will be a matrix with orthonormal columns, hopefully good quality. So that means that Q transpose Q is identity, right? Again, remember, in general, that does not mean that QQT would be identity. unless Q was square. But never mind, we will just need this property. So what we can do is then use the QR decomposition. So instead of A, I plug there QR. Let's assume I computed the QR decomposition and I want to use it to solve least squares problem, this least squares problem. So this means I just substituted the QR instead of A, right? That's my equation number 2. Here I just multiply out the transpose. So this is R transpose Q RX, and this will be RT QTB, right? So I just apply the standard transposition rule. This is something you must remember, otherwise you will not get very far in the midterm or anywhere. And the point of this was that now this revealed the QTQ, right? But QTQ is identity. So this QTQ disappears, so it reduces to identity. So this is just RTR, what I have here, right? And, oh, this is something I did not mention enough, that R actually is full rank. R is invertible. And R is square, right? Let's bring it up again. So the R is square. It's n by n. It's upper triangular. And it's full rank. Why is it full rank? Can someone see a reason why is it full rank? That would be a good exercise, good like problem for some exam. Yeah?
Because there's good elements through the entire diagonal.
Exactly, yeah. And these guys actually all have to be non-zero because the input was linearly independent. Right? So each of them had to contribute something to the new dimension. So all of them have to be non-zero, so they are all pivot elements of this. Yeah, that's right. So this is invertible full rank or invertible not singular matrix. So of course RT, because it's square, will also be invertible, right? And because it is invertible, I can just multiply with R inverse transpose, right, from the left, both sides. So if I do that, or basically just like cancel this, because it's invertible. If it wasn't invertible, I couldn't do that. So this reduces just to Rx equals QTB. And this is nice because this we can now solve easily. We don't need to call any inverse routines because this is just upper triangular. So we can just do back substitution. That's much easier than doing inverse. Yeah?
Can you do this the columns that way linearly independent?
That's a very good question. And to be honest, I'm not sure if you can do it with QR. I think you can with some modified QR thing. But I would be speculating. You can totally do it with SVD. If QR can do it, I don't know right now. I can take a look.
So this only applies if the columns of A are linearly independent.
That's right. That was my assumption there. Yep, correct. So I think it should be possible to modify it so it works also for linearly dependent. But I don't remember it off the top of my head, unfortunately. That was a good question, though. I wish I had a better answer. I can look it up. But definitely once you will like learn SVD, then that can definitely handle all these cases. Okay, so this concludes the Gramschmidt QR least squares chapter. So the next chapter will be like on determinants, eigenvalues, so the cool linear algebra stuff, which will eventually lead us to the SVD, which I'm always mentioning, like the holy grail of linear algebra, because like SVD, all these problems become no problems usually. But now would be a good time to look at the practice midterm examples. We still have a little bit of time, so we can get it started at least. So before I do you have any more questions to this? The least squares, Gramschmidt QR business. If not, then I can bring up this thing. So those are some practice problems because you wanted to see, and I understand I would also want to see practice problems if I was in the other side of the room. And this is what I posted on Piazza, so you should be able. Did you get it? Did you try to download it?
Yeah.
From Piazza? Okay, so you have this document somewhere. So might be good if you have time to look at these examples because you should be able to solve them by yourself, and you should be able to solve them without using any Google or textbooks or anything like that. So that means you really have to remember at least the basic concepts we talked about. What is orthogonal? What is the rank of a matrix? What is reduced row echelon? What is a special solution? It's not a lot of things to remember, but you have to remember them. Okay, so let's take a look at the examples. Actually, let me first give you an overview. So the first one is on coordinate transformations. You did a project on that, so you should be reasonably good at this. And then there's some matrix business, so you might get your hands dirty with some actual matrices. The calculations should be simple. It's more about if you know the ideas, like how to convert a matrix to reduced row echelon, and then figure out the basic properties. This one is similar. And then the second part is about subspaces and orthogonality and some properties of orthogonal matrices, orthonormal matrices. So you can expect a similar structure in the midterm exam. I think the first 3 problems will happen on Monday, and the second 3 problems, there will be 6. There is 7 practice problems. I gave you 1 bonus one because one of them was sort of easy-ish. So the first 3 will happen on Monday, and the second 3 will happen on Wednesday. And on Friday, I think Jake will go with you through the solutions. Any questions? Yeah?
Can you tell us which part is going to be colored?
I think it's similarly structured. I mean, it's not exactly the same, but the structure is, I think, sort of similar like you have in the practice problems. So the first 3 is roughly the Monday-ish thing, and the last 4 in this case will correspond to the 3 problems on Wednesday. Okay. Shouldn't be really too difficult. I guess it's really just about remembering the basic concepts, and you should try to solve some of these problems before the midterm. If this is the first time you are trying to do it on the paper, is on Monday, that's probably not good because you will not have so much time for mistakes, and if you may start panic, and that's not good. Well, you know this drill better than I do. Okay, so let's look at the first example. So this is actually what I mentioned in some of the lectures, but I didn't bother writing out the matrices, so I will bother now. So this is about a simple mechanical system, where I have 3 rigid bodies. So let's look at it actually. And what we need to do is to find a matrix. The task is to find a matrix which converts coordinates from frame A, that's this frame, to some ground frame G. So if I take, so it's just a 2D thing, right? The first thing is to realize that this is just existing in 2D. So my matrices in homogeneous representation will be 3 by 3. I guess that's really the point of the midterm, that it really forces you to remember these things. So if I take a point in A coordinates, then I want to know what are the coordinates of the same point with respect to G, right? And that's what this matrix will be doing, and your task there is to find that matrix. You don't, because this is really not about the non-abstract algebra. This is not about making you compute lots of things. That's not the point at all. So you can leave the answer as a product of component matrices. So you don't have to do the actual math, the multiplying the matrices together. So you know, so this is the problem, right? And how do you go about solving it? You should know this, or give it a second to think about it, or remember how it was done. So the matrix is composed by these elementary transformation matrices, right? I even noted here the frames for your convenience. Maybe you will have to do it yourself in the actual midterm. So the input frame is A. Then I define an auxiliary frame B here. There is going to be some distance between them, which could be called D1 or something. Here is the first angle. So these two things are attached by a rotational join, which has angle θ1. That's one of the parameters of this robot thing. There is another system C. And system D I can actually skip because and do this entire length as just D2. So this is from C to E. It's just the translation along the length of this rigid link. Then there is another rotation of angle θ2, which gets me to F, and then there is some final translation D3 from between F and G. So how would the answer look like? Let me write it down. I can do some funny thing, like keep it here, and then write it here. Yeah, I think I can do that. So we start with GBA, right? So that's going to be matrix which transforms from A coordinates to B coordinates, right? And what this matrix is, it's just a translation by D1. 0, 0, 1. So this is something you have to remember. If you don't remember, you should sort of be able to derive it, right? Just by thinking. The thinking you can do is, if this is my frame A and this is my frame B, I think like some people like Einstein were saying that like rather than like looking it up in like textbooks, they just better like derive it. I guess that was before Google, right? But for the midterm is going to be moot because you cannot Google. If you could Google, it would be about Googling, not about your linear algebra skills. So if I have coordinates of a point P with respect to A, and I want to get coordinates with respect to B, and this is the difference, then, well, sort of makes sense. All I need to do is add to this vector, right? And this is just the length D1, right? And we know that how to do it in homogeneous coordinates. This is the linear part of the transformation. There's the rotational part. In this case, there's no rotation, so it's identity. And the D1 is the translation, right? So this is my GBA part. Now I have to go from B to C. And that's a rotation about θ1. Here, one slight trick is that I actually have to rotate by minus θ1 because I'm doing change of coordinates, which works backwards. I don't know if I need to repeat this. We discussed it during the lecture. That I mean that if C rotates onto B, no, if B rotates onto C by rotation θ1, by angle rotating about angle θ1, then the change of coordinates from B to C is rotation by minus θ1. If you don't remember it, then now I can take advantage of the YouTube thing. Then just go back to the lecture where I was explaining it. I don't want to go through I cannot go all this again. I only have a couple minutes left, and I want to finish this. So this is GCB. Then I said I'll skip these and I will go directly to E. So GEC is very simple, right? It's this. This is from C to E. That's again just translation. Then going from E to F is another rotation, so that's the same thing, just with θ2. And finally, going from F to G, that's just a translation by D3. So the final matrix going from A to G is product of these matrices and that is the answer. You could multiply it all together if you like matrix multiplication, but I said that you can leave the answer as a product of component matrices, so this is a perfectly fine answer. Okay? That's problem number 1. Any questions? So what about problem number 2? Let's take a look. Yeah, actually, I don't think I'll have time to do the entire problem 2. So I guess if you want to prepare well for the midterm, then try to solve these problems by yourself. And on Friday, I will solve them for you. So actually, it's very, very helpful. If you first try it and then see the solution, it's a totally different experience than if you don't try it and just see the solution. Because maybe you get stuck on something and then you will realize, oh, it was actually super simple. Or maybe there was something that's not so simple, right? It's like playing chess. Like the hard part is to find out which part is worth your time. Okay. All right, so I'll see you on Friday. Thank you.